Leave a bowl of soaked raisins on the kitchen counter overnight, and you will find a curious transformation. By morning, the raisins have plumped up. They have grown larger and heavier without any stirring or heating. This raises a question about the physical boundary of the fruit. How did the water penetrate what seems like a sealed skin? And if the water could get inside so easily, we have to wonder why the concentrated sugars inside the raisin didn't simply leak out into the bowl. This transformation shows water molecules crossing a boundary in a single direction, following a silent migration that hints at a deeper physical rule. The microscopic structure of the raisin's skin is a highly specific security checkpoint. This is a semi-permeable membrane, a selective filter that allows tiny water molecules to slip through the gaps while blocking anything larger. While water moves freely, the much larger sugar molecules are physically blocked. They are trapped on one side of the barrier. Outside the raisin, the water is pure. With no sugar to get in the way, these molecules have a high degree of freedom to move. Inside, the environment is crowded. The water molecules here are occupied, chemically tied up by their interactions with the trapped sugar. This difference in molecular freedom creates a thermodynamic imbalance. To regain stability, the system must find a way to correct the difference. The system corrects itself by drifting molecules from the free region to the occupied region, attempting to balance the concentration on both sides. This is the mechanical process of osmosis, the movement of solvent molecules through a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. As water floods into the raisin, the volume increases. This creates immense internal pressure. The raisin's semi-permeable skin stretches outward to its absolute physical limit, eventually pushing back fiercely against the constant rush of incoming water. This resistance is called osmotic pressure. It is the exact amount of outward force required to perfectly halt the flow of osmosis. This shows that osmosis is a dynamic negotiation, a process that continues until the inward pull of concentration and the outward push of pressure reach an equilibrium. The pursuit of equilibrium governs critical life functions everywhere. Deep underground, microscopic plant roots utilize these exact concentration gradients to silently extract vital water from the surrounding soil. In our own bodies, red blood cells swell or shrink in response to the concentration of the surrounding fluid. We see the same logic in historical food preservation. Packing meat in salt or sugar draws internal water out of microscopic pathogens, dehydrating and destroying them. Modern water purifiers use high artificial pressure to overpower natural osmotic pressure, forcing water backward through a filter to leave impurities behind. Watching a raisin swell in a bowl means seeing water balance chemical differences, a mechanism that drives life from the kitchen to the deepest cellular level.